Hello again. Is the camera crooked? Maybe a little bit. Okay. And I have some chalk from climbing today. Anyway, topic for today is sigma delta, oversampling and sigma delta ADCs. And let's dive in. So, first of all, it's good to understand why. So I'll go through a little bit about the state of the art within ADCs and then introduce the topics of oversampling and sigma delta, or delta sigma, or noise shaping, or whatever you want to call it. It is really how do we tackle or handle quantization noise. But for ADCs is a cool IP because it's one of the few analog blocks you can design in isolation. You can define an input impedance, and as long as you do define the input impedance roughly correct, you can sort of reuse the same ADC multiple places. So it's a very common design that you'll see in papers, and it's always interesting with a better analog to digital converter. Now, back in '99, a guy called, I think the first name is Robert, I might be wrong on that, Walden, he did a survey of ADCs at that time and made this beautiful plot. And what we can see in this plot is we can see the dots here are the ADCs for different sample rates. So higher sample rates, you get lower signal to noise or lower number of bits. And then adding in the thermal noise line, aperture, not entirely sure about that, might be jitter, I don't know, ambiguity, and then Heisenberg's uncertainty principle. Okay. I think the video is still running. Now, a guy called Boris Murman, who's a professor at Stanford, he updated this survey, and he continuously now tracks the best of the best ADCs in the world. And they are published at ISCCC and VLSI Symposium. And, well, some are also published in other solid-state circuit conferences, or indeed in the Journal of Solid State. And we can sort of see that there is continuous push for better and better ADCs, but there are some fundamental limits for a figure of merit. Now, the figure of merit that Walden defined was the power consumption of the ADC divided by 2 to the number of bits times the sampling frequency. And here, if you get close to 1 femtojoule per conversion step, that's fantastic. I think on my PhD I did 1 picojoule per conversion step, but there is continuous improvement in the ADC performance, and that's sort of a good number. It also means that if you know the number of bits, if you know the sample rate, you can actually estimate the power consumption that is possible to make. It depends a bit on the bits, because it turns out when you move into higher number of bits, the performance of the ADC is actually limited by thermal noise, and it's not that much about the circuits or circuits parasitics anymore. And then it sometimes makes sense to use a different figure of merit. But know that at NTNU, we have had PhD students, we have had postdocs, we have had people that have made some of the best ADCs in the world at the time. These are 2 examples. So one published in Journal of Solid State, the other one here I believe was published in Asian Solid State Circuit Conference. And you can sort of see they rank among the best. Of course, now today they've been succeed. Well, I'm not sure. They might have been improved upon by others. When we move into the higher number of bits, 14, 12, 14, 16, and so on, then, as I said, the thermal noise becomes more important. And it's actually better to use a different figure of merit, and here it's usually called the Schreier figure of merit. So Richard Schreier, I believe, he is from Toronto, I think. Well, at least that's, I believe, where he spends his time. And he defined the this figure of merit, that is the SNDR plus 10 log fs divided by 2 times the power. Now, this is a better figure of merit because it actually scales with thermal noise. The Walden figure of merit, if you add 1 bit to your conversion, you can sort of spend double the power and still achieve the same figure of merit. But if you're limited by thermal noise, then you actually have to increase the capacitor size by a factor of 4 every time you add a bit. And that would increase the power consumption by a factor of 4. And that's covered in the Schreier figure of merit. Now, quantization. Very simple. Not really. Quite hard. But the principle is easy. So we start with an input vector. This is a discrete time vector. It is continuous in value. What we want to create is a discrete time, discrete value signal, a digital signal. Now, we can define this process as adding a certain noise to our input signal. Because if we quantize the value of the x in a certain number of levels, then our output y will have errors. It will not be exactly the same as the input at all times. And we can illustrate this by a sinusoid in the blue curve, and then the red curve here is showing our y. So here we quantize, we sample and we quantize our input at certain points in time, which means that there will be an error in the output from the actual input error. Now, we can sort of plot this error. Let's see, what have I done here? So the red, I think, is still the y. Yeah, anyway, I'm plotting the error signal that we sort of add for a given point in time. And this quantization noise has some interesting properties. You might not find it in the book. I found this information in a data converter book. Unfortunately, I don't remember the reference right now. But anyway, it turns out it's possible to work out mathematically that the quantization noise is actually a sum of harmonics of the input signal. So P here is the harmonic index, and it turns out to be this sum of Bessel functions of the first kind. Don't ask me what that means. It's some maths thing. I'm sure if you wanted to work it out, you will find it in MATLAB or some other. You could also find the information in the paper here. Let's go to that. So it actually shows the derivation of these, what the quantization noise is. And this is actually quite important. I'll explain why in a minute. But we can approximate the amplitude of the input signal as 2 to the power of n minus 1 divided by 2. So that's sort of the scale of the input signal, the amplitude of the sinusoid. And if we do that, we can work out the full equation. Now, I don't expect you to use this equation, but I do want you to understand the consequence. So, and the consequence is, although the quantization noise, we quite often say it's random, so like uniform distribution, not uniform, it's actually let's see, in frequency it's flat. So it's a white noise. That's our assumption, but actually quantization noise isn't white. It is an infinite sum of harmonics of the input signal. That means that it is actually a nonlinear function of the input signal, which means it's not white. But to a certain extent, we can make that approximation if you have enough bits. We'll see why, or see the effects of that. Now, if you work out what is the power of the quantization noise, you can show that it's roughly the LSB, so this is the delta, that's the least significant bit, squared divided by 12. And if we know then our quantization noise power of this error signal, we can, well, we know the power of the input signal, so amplitude squared divided by 2, and we can divide that by the power of the quantization noise, take 10 log, and, well, work through the maths, and we can actually show that what we call the signal to quantization noise ratio is a function that is 20 times the number of bits times log 2 plus this factor here, 10 log 6 fourth. And that can be approximated by signal to quantization noise ratio is roughly 6 times the number of bits plus 1.76, and the 1.76 is making the assumption that we're using a sinusoid as a test signal that has a signal power of a squared divided by 2. So this is useful. If we know the dynamic range that we require for an ADC, for example, let's say 60 dB is what we need. That's the resolution that we, or the dynamic range that we need for our ADC. We can translate that directly into roughly 10 bits. What I've done in this slide is try to demonstrate how quantization works and how this error signal looks. I start with a, let's assume it's a continuous time, continuous value signal. It is not really continuous time, continuous value, because I made this on a computer, and a computer is digital. And let me go full screen for this part. There we go. So I've added some noise because our input signal will have noise, and a sinusoid. So this is around 0. There's one sinusoid. And then I sample. I convert it from continuous time to discrete time, or model that as we saw last time for switch cap. That gives us a discrete time continuous value. And notice here that the noise floor for our now sample spectrum, so now we're taking sort of a chunk, we're only looking at a portion of our spectrum, so the frequency axis has reduced. The noise power actually increases. And the reason for that is that all the noise that is outside our sampling frequency, that folds down into our band. So it's sort of, let's see. So noise out here will fold down into our band of interest. Okay, and now we put it into an ADC. Here I've used a 1-bit ADC. Only 1 bit. Which means that our error is going to be quite large. Our signal to quantization noise ratio is going to be crap. But the reason I do this is you can actually see that the noise floor here, it is not white. You can see the harmonics of the input signal. Now this is an infinite sum of input harmonics, which means that the harmonics that are above our sampling frequency would actually fold down in band. But clearly this the spectrum for the 1-bit conversion, so this is actually taking a FFT of the digital output, the digital 1-bit output, and that is clearly not a white noise spectrum. So we have our sinusoid and we have a lot of noise, and that noise has signal content. So that's why I say it's important to know that the quantization noise is not white noise. It is harmonics. let's say we increase the resolution to 10-bit, and then the quantization noise level drops, because remember the power of the quantization noise was the delta, so the LSB, least significant bit. And if we increase it to 10-bit, it goes from 1 over 2 to 1 over 1024, so that's obviously lower. And now we can see the spectrum looks more like a white noise spectrum. It is flat across frequency. Okay, now we're into the digital domain. Now we created a digital signal that represent our analog inputs. And it turns out we can also use something called oversampling. Now, oversampling is a method of reducing the in-band quantization noise. So let's assume that we used a Nyquist ADC and we actually had quite high sample rate compared to the band of interest. So for example, maybe we have an ADC that runs at 100 megasamples, but we're really only interested in 10 megahertz bandwidth. Then we can oversample, so we can actually average the noise, the quantization noise. And if we average the quantization noise, we reduce the quantization noise power. Now that's just divided by the oversampling ratio. So here, an oversampling ratio of 2 is basically reducing the sample rate by half. And we can work through the equations again, and we can see that for every doubling of the OSR, so when we go from 2 to 4, we get a 3 dB better SNR, or SQNR, signal to quantization noise ratio. So you can actually increase the resolution of your band of interest by oversampling. Caveat: you need to have an output signal that varies. For example, let's say you make a 10-bit ADC and you make the thermal noise level so low that you take one sample, you get a value, for example 100. You take another sample, you get the same response, 100. You take another sample, you get the same response, 100, because you don't have any thermal noise in your system. In that type of situation, averaging wouldn't help you. So you actually need to have variation in the digital output code to be able to average. Now we can also do this in Python. So here I have an oversampling function. It gets a vector in and it has an oversampling ratio. So I just compute the length of the vector. I initialize my output vector, and for each of the samples in the input vector, I sum for over the OSR range. I sum, let's call it OSR number of samples. So if the OSR here was 2, I would go k equals 0. So I take m equals n plus sample k, and then actually here you can see it. So the output vector is the sum of the 2 next samples, for example. Now this is actually kind of like a finite impulse response filter. We are summing digital values and we are summing a couple of them, or OSR number of them. And if we then look at the output spectrum, we can see that after conversion to 10-bit, we get a flat noise floor, but we can actually average the noise. And by doing that, we actually reduce our quantization noise floor. Because now if I reduce the bandwidth or downsample my digital signal, when the noise folds, I will get less of the in-band, or the quantization noise will not increase that much. So I can actually reduce noise after I've converted it to digital. And I can continue to OSR of 4, which gives it another notch in the frequency response of the noise. But here you can also see that if I go with a high OSR ratio, then at some point I'll reduce my input signal. I'll start filtering my input signal. So oversampling, pure oversampling is useful, but it's not perfect because at some point, yeah, you can't really increase the resolution that much. Now this is interesting, I find, because maybe we could do better. Maybe we could do a trick, because we have sort of three steps: continuous value, continuous time, continuous value. We have discrete time, continuous value. We have discrete time, discrete value. Maybe we could do something in between discrete time, continuous value and discrete time, discrete value to improve our noise floor. That's where noise shaping comes in. And now this is just fun and interesting. Okay. In any given feedback system, we have an input. Let's assume we have an input, VI here. And we take our previous output, VO, and we feed it back to subtract from the input. So that means the Vx in this graph, or this picture, is the difference between our output and our input. And then we amplify the error in a filter. Now, an interesting thing happens if we set up the equations for this. So let's see, Vx is Vi minus Vo. Vo is equal to Vx, h of s. And we can work out that the Vi is equal to Vo plus Vo divided by h of s. Now, if we make h of s infinite, then our output will be exactly the same as our input. This is sort of a principle of negative feedback. It's similar to the concept that we use in our op-amps. Okay, so that's cool. Now, of course, making an h of s, a filter here has an infinite gain over all frequencies is not possible. But maybe we can make it infinite at certain, or not infinite, but really large at some frequencies. Because if we expand this idea and add an analog to digital converter in the loop, so we have the same situation. Vi comes in. We take the in this case, we take the VO is actually a DAC. So it's an analog representation of our digital signal. And then we take the error between the current input and the previous output, and we put it through a filter with a high gain, and then we convert it to our digital value. Then we can actually get a similar situation. Now, before we jump to the next slide, it actually means that if you were able to make the transfer function of this h of s infinite, assume you can actually have infinite signals, because it becomes a bit of a problem with the signal swing at the input of the ADC if the gain here is infinite, because if you have any error signal, the output signal here becomes so high that it goes to VDD and things doesn't work anymore. But in principle, we can make our digital output an exact representation of our analog input. This is the principle of noise shaping, because it doesn't matter that much what the ADC noise is anymore, because it's after a lot of gain. So this is the structure that you'll find in every single audio analog to digital converter. It is the same principle that you will find in digital to analog converters, and especially the ones that are using a 1-bit analog to digital converter. So what happens to the equations? Now, in the picture on the left here, I've actually mixed a bit frequency domain, or not frequency domain, but Z domain and sample domain. Ignore that for the moment. But this is a similar type of system. We have our ADC, which adds some quantization noise. We have an input to the ADC, x of n. We have the input to the whole modulator. Quite often we call this the modulator. Actually, I shouldn't call this plus here. We can call it a quantizer. It quantizes the digital, quantizes into digital levels. And then we have feedback. Now the feedback would of course include a digital to analog converter. But we can set up the sample domain equations here. So we have the output, the y of n, is equal to the noise that we add in the quantizer, plus a convolution of the impulse response of this h of z filter with the difference between the input signal and the output signal. Now, if you translate it into the z domain, the convolution becomes a multiplication, and we can actually work out a couple of equations. So quite often it's common to talk about signal transfer function and noise transfer function. And what we mean by that is what is the transfer function from the signal at the input here to the output, and what is the transfer function of the noise from E of n to the output. So we can work out the signal transfer function to assume that if we assume that the input signal u and the error, the quantization error, is uncorrelated, and we can also assume the E is 0, then we can work out that the signal transfer function is equal to 1 divided by 1 plus 1 over h. And here we can see if we make h here really, really large, then the signal transfer function becomes 1. Same for the noise transfer function. If we assume the input signal is 0, we can work out that the noise transfer function is 1 divided by 1 plus h. Now, that means that if we make the h really, really large, the noise will be quite low. So combined, we sort of, in the z domain, we multiply the input signal to the modulator with the signal transfer function, and the noise transfer function, we multiply that with the noise. Now, if we make, let's see, so if we make h really large, the noise transfer function will become really, really low, and we can filter a lot of the noise. Now, as I said before, we cannot make the h of z infinite at all frequencies. It has to have some roll-off, because we get into stability issues. We simply can't have enough voltage swing in our actual circuit. But we can get close. So let's assume that our h of z is an integrator, and we can work through the equations. And if we make, well, we insert for the z, we can actually work out what the noise transfer function will be. I don't think I have a plot of the noise transfer function, but you can plot the 2 sine pi f divided by fs into any calculator, and you will see that it actually suppresses noise, quantization noise, at low frequencies, and it increases it slightly at high frequencies. It's also a good description in the book on this exact derivation. But the main point is that if you work through all the equations, we can now look at the signal to quantization noise ratio for a first order noise shaping system. So then we have one integrator, sort of not one feedback loop, but one integrator. And we can see that for every OSR, instead of having 10 log as we had for oversampling, we have now 30 log. Now that means that it increases much faster. We can add a lot more bits for a doubling of the OSR. For a first order quantizer, or actually 1-bit quantizer, we can have a look and see what happens. So 1-bit quantizer, I have oversampling, and I have an oversampling ratio of 4. That means the maximum ENOB, or effective number of bits, would be 2. for a first order signal delta, it would be 3.1. For a second order, it would be 3.9. So of course, there's not much difference. But if we go to an oversampling of 1024, we get 6 bits ADC, or resolution effective number of bits, for the oversampling. We get 15 bits for first order sigma delta, and we can get 23 bits for a second order sigma delta. So the second order means the H of S has, now I have to be say it correctly, the H of S has 2 infinite points. Or said another way, the noise transfer function has at least 2 zeros. I guess H of S would then have two poles. So how does this look when we implement a sigma delta in Python? We can do that, of course. So in that case, we can add some dither. I'll speak about that later. Dither is important, especially in low bit modulators. But for now, let's ignore it. We take our input vector, x of Sn, figure out the length. We initialize a couple of vectors to represent our output vectors and this intermediate step inside the modulator. And then we iterate over the index in the input vector. And then we take our current x of n is then equal to the previous x of n plus x of n minus the previous output signal. So this becomes an accumulation. It's like an integrator. And then we quantize the output signal by just rounding x of n times, well, 2 to the power number of bits. And then after the rounding, we divide it by the number of bits again. The dither part here, this vector, or actually this option, is to turn on randomization on the quantization. And the reason for that hails back to quantization noise. Since quantization noise is not a random thing, it is actually signal dependent, then it can be important to add some randomness, actually add noise at the input of the quantizer to make sure our spectrum looks pretty, or you will see it very soon. Okay, so now we have a sigma delta modulator. We go from continuous time, continuous value, discrete time, continuous value, and the plot number 2 here. And then for the third plot, we go to discrete time, discrete value. So that would be our regular 1-bit quantization. I've also added now the noise shaped version. And here you can see how the noise have been shaped. But we can also see that it didn't really improve our signal to noise ratio close to our signal that much. And that's because the quantization noise of a 1-bit quantizer is not white. But if I turn on the dither, you can actually see that increases the noise level a little bit, but clearly the signal to noise here is much better than the signal to noise in just the quantized version of the input signal. And this is why it's also called noise shaping. So we shape the quantization noise such that we increase the quantization noise outside of the band, but we decrease it within our band of interest. Because we can easily add oversampling, or we can easily add filters, brick wall digital filters for the output of this modulator, and then filter away the noise in the higher parts of the spectrum. And that brings us back to the slide I showed a while ago. This continuous time quadrature cascaded sigma delta modulator with blah blah blah. Okay, so here we can recognize we have our input signal. This is actually a complex ADC, so it has differential input for the in-phase signal and a differential input for the quadrature phase signal. The only difference between these two inputs is that the quadrature would be 90 degrees offset, or delayed in time. This is very common in radio receivers. And then we have an output signal here at Y1i and Y2i. That's the output of the ADC, and that's the signals that would go to a filter to filter the noise. And then we can see we have ADCs feeding, this is sort of a two-stage, I guess. So you have, let's see, so this is one pole. This might be a second, I'm not sure. Let's put a passive. So this is at least the two-stage, maybe a three-stage sigma delta, and it's actually a cascade of two of those. So I guess, does it say? No, it doesn't say the order of the modulator in the slide, but you can figure that out in the paper. And then we can see the DACs that go from the output signal back to our input, and then it's the error that is fed into the filter. So the ADCs here are the quantizers. Now we sort of quantize in two steps. So we quantize one time first, and then we send the error signal from that quantization onto another sigma delta modulator, and then quantize a second time. This is quite common. Now, what is cool with this quadrature sigma delta modulator is that we can actually shift our noise transfer function in frequency, so we only reduce the noise, quantization noise, for a certain band that is actually not centered around 0. And that's possible because it's complex. So this is kind of like a band pass sigma delta modulator. Now the signal transfer function is the one we see in the dotted line, and that we can see is equal to 0 dB, so 1 in the band of interest. And then the noise transfer function is, well, I guess, I don't know what the magnitude here, but we can actually get 77 dB dynamic range, which should translate to about 12 bits, roughly, ish. Yeah. Pretty cool. This is a continuous time. So it has continuous time input, discrete time output. It is possible to do discrete time sigma delta modulators with switch cap circuits. And then you have the continuous time to discrete time conversion before the ADC. The advantage of continuous time ADCs, like the one shown in the picture here, is they have inherent what we call anti-alias, so they will filter some of the signals far out of band, which makes it easier to, well, both easier to drive, and we don't need necessarily an anti-alias filter in front of the ADC. Now, sigma delta modulators don't have to be as complex as the one you're looking at now. I would assume if you were actually going to make what is shown here in the picture, in the integrated circuit, I would assume it would take roughly a year working full time, and I would put maybe a couple of designers on it to design. So a couple of designers to do the actual ADC, and then I need a digital designer to do the what's called a decimation filter, or the filter after the sigma delta modulator. So this is quite complex. It's possible to make them easier. I'm going to show you one. So this, actually, let's open this picture, and let me just scale the screen. My computer is complaining. I need to buy a new one. Okay. Does that work? Yeah, This, no, that's too small. Just a second. Can we make it bigger? There we go. That's better. That's not better. That's a lot worse. Okay. Let's try again. Sorry about this. Oh, cool. Let's close that down. Go back. Click the link again. See if we're lucky. Click the picture. Okay. And let's stop. Now let's just download the patent. Where's download? Download. Okay. What is shown in this picture is an ADC I made back in 2010-ish. Yep. And this, what you're seeing now is a sigma delta modulator. It has an input that is continuous time, and it has an output which is a 1-bit output, which is discrete time. The way that this works is the op-amp will ensure that the two inputs, Vx and Vref, are the same. So Vref is our reference voltage, and divided that by 2. So Vx will also be Vref divided by 2, which means my input signal will be a current. So the resistor will translate the input signal into a current. That current will be integrated on the capacitor, and here it's added a sort of a offset current to ground to get the common mode at the input, so where the input swings around at the right level. Now the reference or the feedback DAC is shifting between the reference value and 0. So that adds current either into the Vx node or out of the Vx node, depending on the output of the comparator. And the comparator is our quantizer. That turns the Vout value as soon as it crosses the Vref value here, Vref divided by 2, the comparator will go high, and we will then feed back a DAC value that pulls the that discharges the capacitor again until it crosses VO, and then we charge it up again, and so it proceeds. So this is a 1-bit sigma delta modulator that you can make if you wanted to. And you can get, if you do it right, and there's a couple of tricks in here. Fuck it, let's mention them. So first of all, the comparator needs to be dithered. You need some dither. This is a 1-bit comparator. You need some noise to whiten the quantization noise. That's the first important part. The second important part is the reference resistor here will have a parasitic capacitance. So every time you switch the reference from Vref to ground, the parasitic capacitance can actually pull a little bit more charge because you need to charge the capacitor, and that can give a signal dependent current feeding into our integrator. Now, this ADC is actually a what we call an incremental sigma delta modulator. So that means we reset the capacitor at a certain time, and then we run the sigma delta modulator for a certain number of samples, for example 1024, and then we average all those 1024 outputs, which gives us a digital value. So we can then do 10-bit or 12-bit, but of course it takes a lot of time. So that means you can actually use a sigma delta modulator in incremental mode as an Nyquist ADC. Yeah, you can, the link's in the slide, so you can look more into that. Okay, thank you. Have fun. And don't expect that this video will teach you everything about sigma delta modulators. Segmented modulators are hard, especially complex ones. People have spent their masters, PhD, postdoc, and the rest of their life on segmental modulators. But they're really cool. And making better ADCs is always good, because that means we can do new cool stuff. Bye-bye.